What if I gave you this circuit and I asked you for these voltages, Vx, VDA, VCA, VBD? Would you be intimidated by the circuit? Maybe you already find it confusing. I think a lot of beginners at circuits find this confusing. So I'm going to help you think about this. And to do this, we're going to first take a look at another analogy that can help you grasp this. Let's start with a landscape. And let's say there are some cities here. We could think of some sort of elevation for these cities, some height. We could say, define HBA. So let's put up here, HBA. This is the elevation of B relative to A. And I'm going to highlight this relative to A part because whenever we talk about an elevation, it's always relative to something. Normally, we say a city is at 8,000 feet, 5,000 feet, 2,000 feet, and that's relative to sea level. So it's always relative to something. And here we're saying, B is the point of interest and A is the reference. So HBA is the elevation of B relative to A. So we could also write HAB, and this is the elevation of A relative to B. And I could say, for example, the HBA is 200 feet. And then if I told you that the elevation of C relative to B is, that's 400 feet, well then we could write here that HCB is 400 feet and HBC is negative 400 feet. And I didn't write it in, but we would say here, well, okay, HBA is 200 feet and HAB is negative 200 feet, right? Because A is 200 feet lower than B, so its height relative to B is negative 200 feet. And then it's trivial to say, well, the height of A, actually let's make that the height of C relative to A. Well, we know that there's a 400 and a 200 there, so it's 600 feet. And you could see that because you could add HCB along with HBA. So the elevation of C above B added to the elevation of B above A. There's another way to think about it, and just think of it as y coordinates. That distance is HCA. So you could think of it as HC minus HA, but the thing I want to point out here is C does not have its own height. Like it's not an absolute property of C. This is a relative property, relative to sea level or relative to something else. In fact, what I'm going to do is I'm going to go relative to B, for example. So in either case, a common reference is needed. If you're going to think about it as a subtraction of heights like this, and using what we know, HCB is 400 and HAB is negative 200 feet, and so that's 600 feet. And so that agrees nicely with our previous result, which we did intuitively. What I'm really trying to get at here is that voltages in a circuit really are about two different points, just as every elevation is two different points. So you can think of voltage as a landscape in a circuit. Now, technically, voltage is the potential energy difference per unit charge between 2 points. So we can stress, right, if there's a difference, right, difference necessarily implies 2 points because you're comparing two things. And so that's what a voltage really is. Armed with this knowledge in this previous analogy, let's attack this circuit. So it's helpful if you identify the nodes. So this actually is A. It's not just that little point here, but it's that entire electrical connection is A. And that's all at one voltage. It's all one elevation, if you will, in the potential landscape of this circuit. Node C, node D. Again, each node is at its own elevation. Any 2 points on that node are all at the same elevation. Let's just start with Vx. Well, Vx as you can see, this connects nodes A and C, and Vx measures the height that A is above C. Why? Because of the plus sign is associated with A. The minus sign, or the reference, is here. So we'll put here Vx is equal to VAC. Now, you can do a Kirchhoff's voltage loop. So let's draw that in. We're going to do a loop all the way around, starting at, say, A, and then coming back to A. And as we go around our loop, starting at node A, we have negative Vs1. Oh, I don't like that. I'm going to erase that equality sign there. Negative Vs1. Oh, and I need to fix my circuit here. Let's fix it. This should be a Vs2. So negative Vs1. And then now we've gotten to node B. At node B, going to C, we have a plus Vs2. So the way we think about these is we're adding up voltage drops. So when we go from B to C, we've dropped Vs2. And then when we go back from C to A, we drop again, but it's a negative Vx1, or Vx, that is what we dropped. And that's equal to 0 because we're back at node A. And again, if you go take a trip among these different cities and come back to the same point you initially started, what's your elevation change? Well, it's 0. That's what's going on here, is we've made a full circuit back to the same elevation point. Elevation change is 0. So now we can move Vx to the other side. And we'll put here Vx is negative Vs1 plus Vs2, or Vs2 minus Vs1. Another way to look at that is, again, just using these relative heights. So we'll put here Vx equal to VAC, and we could add VAB and then add VBC. Well, we know that VAB, right, because of this voltage source, so we know that as we go from A to B, we rise Vs1, or another way to say it is we drop negative Vs1. So we'll put here the voltage drop from A to B is negative Vs1. Why do I think about voltage drops? Well, because when we say A to C, we're asking how much higher is A than C. The other way to think of it is what's the voltage drop when we go from A to C. So we go from node to node and we add up voltage drops. So the first voltage drop from A to B is negative Vs1. And then the next voltage drop from B to C is Vs2. And so you can see here that our two solutions, when we use KVL and when we do this maybe more intuitive version of just adding up voltage drops, is the same. So we have Vx. And because Vx is VAC, we could also then write that VCA is negative VAC is negative Vx. And so we could easily write that as Vs1 minus Vs2. So now we have VCA. Now how about VDA? So that's the voltage drop as you go from D to A. I actually want to come back to that because maybe we can get VBD first. We'll draw another KVL loop in here, starting at B, going to C, then back to B via D. So what I would have here in this loop, and let's put in here VBD, and just for completeness, the plus side of this voltage goes here. Oh, I'm sorry, I actually had that backwards, because we're thinking of D as the reference, so the minus goes with the reference, and the plus goes with the point of interest, the B, so VBD. How much higher is B than D? Okay, so following that KVL loop, starting at B, we have a negative Vs2, actually that's a positive Vs2, B to C, right? Positive Vs2. And then if we think about the current, we want to get a voltage across R2. So we think about the current. Well, the current's going to go here into the plus side and out the minus side. So the plus side's the high side, the minus side's the low side. So we'd say this is IS R2. That's the voltage. So going around our loop, we hit the negative side first as we follow the KVL loop. So we're going to put a minus IS R2, and then a plus, actually that's a minus, my mistake, minus VBD because we encountered the minus sign first. So minus VBD equal to 0, and that gets us VBD is equal to VS2 minus ISR2. So we've got VBD, and now we can do VDA by adding up voltage drops as we start from D and then go to A. So I could go VDB and then VBA. And so we already know VDB, right? It's negative VBD. So let's put in here negative VBD. And then VBA is VS1. So we'll put here negative VBD is ISR2 minus VS2. And then we add the VS1. So that's our VDA. We could also take this and say, well, this is VDC plus VCA. So that's going from D to C and then C to A, adding up voltage drops. And what does that look like? Well, we already know that VDC is ISR2, and then VCA, which we got before, is VS1 minus VS2. And then if you compare results with the two different paths that we took, they agree. So that's good. That should make us feel like we know what's going on. Briefly, I just want to discuss some things that I see as common misconceptions, common misunderstandings. The first thing is maybe not understanding voltage. People forget that 2 points are required. Another thing that I hear students talk about is they talk about voltage flowing. It's the current that flows. Voltage is more like an elevation. So I really want you to get the words right because the words affect how you think about it. And so if you get the words wrong, then you think wrongly about the subject and it confuses you. So let's think of voltage more like an elevation. And the last error I would like to show you is something that's pretty common. And because of what we just went through, it might be clearer to you. So let's draw a circuit really quickly. A lot of students are tempted to say that I is equal to Vs over R2. And why not? Because, well, V is equal to IR according to Ohm's law. Well, there's a V and there's an R, so that's great. Well, there's a problem with this, and you can start to see it if you look at the nodes. There are 3 of them. Label them A, B, C. With Ohm's law, what we need for the V equals IR, well, we want the current through R2, but we need the voltage across R2. And that voltage would be VBC. So I is VBC over R2. Now look carefully at what is going on here. We see that VS connects A and C. So VS is equal to VAC, and it's not equal to VBC. Therefore, it's inappropriate to use VS with R2 when you're looking for the current. You have to use VBC to get the current. Another thing you can do, right, is since the current is flowing from A to C, it's all the same current. Well, you could use I is equal to the voltage from A to C, but now you have to include all the resistance from A to C. So VAC, in fact, is VS, right? So these are the same. But the resistance from RAC, it includes a series combination of R1 and R2. That would be the current. So that's the thing is, you know, if you've got a resistor, let's just summarize this, R, and you have the nodes X and Y, and you have a current, let's call it I, X, Y, because that's the current flowing from X to Y. Well, you need Vxy in order to use Ohm's law properly. The other thing you could do is, of course, you could go the other way, right? You could use Iyx and you would have Vyx. And Vyx is the negative of Vxy and Iyx is the negative of Ixy. So there are negative signs that cancel, and so these two expressions are equivalent. So I hope that clarifies and helps you avoid yet another pitfall. You have to use the correct voltage. You can't just use any old voltage that you find in the circuit. It has to be the voltage across the resistor to get the current through the resistor. Okay, hope that helps and hope that clarifies things for you. Know the nodes, love the nodes. They'll take care of you.